All right. So a lot of topic 2 is stuff that you learned in 10th grade and 11th grade. So hopefully we'll be able to kind of go through this quickly. But the first kind of theme here is I call atomic structure. Okay. And what I mean by that is just understanding the subatomic particles that are present in the atom, how to calculate them, how to determine how many there are based on information that's given to you in the problem. Okay. And so obviously we have our proton, our neutron, and our electron. Okay. And we know the proton and neutron are located densely packed nucleus, and the electrons are orbiting around in an electron cloud around that nucleus. The relative masses of these particles you also need to know. A proton is 1 atomic mass unit. A neutron is approximately 1 atomic mass unit. An electron is about 1/1860th of an atomic mass unit, which is why electrons are negligible when we talk about the mass of a whole atom, because they're so small in mass relative to protons and neutrons, they don't really have an impact. And so when we look at an atom, we generally base it just on a proton and neutron, which usually makes the atom's mass a whole number. And so you say a carbon atom has a mass of 12, or a carbon atom has a mass of 13, because you're just counting how many protons and neutrons are present in there. Okay. The symbol that lets us know how many subatomic particles are in an atom is what we call the nuclear symbol notation. Okay. Okay. And this, with the generic symbol, looks like this. Okay. I'm gonna move this over a little bit. But a real symbol would look a little like this. Okay. And there's 4 parts of this nuclear symbol that you need to be familiar with when you're breaking this down. Okay. Number 1, the atomic number. Okay, which is notated by Z. I know it's ironic that there is an A here as well, but Z is atomic number. And a lot of times the IB on multiple choice and short answer questions, if there's an element that's not really familiar or common, they'll give you the atomic number so you can find it more easily on the periodic table. So um, like even copper, they might say Z equals 29. So that way you don't have to hunt for the element on the periodic table. That Z equals 29 goes, oh, I just need to go to the atomic number, it's 29. And that atomic number gives us the number of protons in an atom. Okay. It may also give the electrons based on the charge, but I'm going to save that for another part as well. 18 is our mass number. Okay. Our mass number is our protons plus our neutrons. And since our atomic number is our protons, then if you subtract these two numbers, you should get the number of neutrons in any atom. So as long as you subtract the two numbers down, you will always get the number of neutrons, no matter what. There's no exception to that. Another logical aspect of this is because the mass number is always the protons plus the neutrons, the mass number should always be larger than your atomic number. So the larger number always goes on top. And so if you know the bottom number is the atomic number, then the only other thing that gives mass is the neutrons. So the difference between those has to be the number of neutrons in your structure. So the large number is always the mass number in this symbol, because the mass number includes protons, so there's no way it could be smaller than that. And lastly, our charge, okay? The charge essentially tells us the difference between electrons and protons. So our charge tells us how many more or fewer electrons we have compared to our protons. And that's why the sign is important, and that's why the quantity is important. Okay. And so if you want an equation to think about, I would say this: the protons minus the electrons equals the charge. Because remember, protons are positive, electrons are negative. So therefore, if you have more electrons, you'll get a negative number. If you have more protons, you'll get a more positive number. Just don't subtract a negative. Okay, just subtract the number. So in this example, 2 minus tells you that if you have 8 protons and your charge is 2 minus or negative 2, then X has to be 10. So you have 10 electrons in this structure. Okay. Questions about that? Any clarifications? Yes, Lamar. Oh, sorry. You're right. Sorry. It is P plus. Sorry. I don't know why I was writing 0. It is P plus. I was just getting the habit with my neutrons for some reason. Yeah. Oh, it's a charge, right? So proton is P positive, electron negative, neutron 0. I don't know why I wrote 0 for that. Thank you. Yeah. We'll edit that out of the video. I can't show weakness. Okay. So in this structure, this oxygen atom, what we can tell is this. We can tell the mass number is 18. The atomic number is 8. Protons is 8. Neutrons is 10. And electrons is 10. I did again with the 0, sorry. I think I've just been so used to all the subjects we've been talking about is every time I have a superscript, it's usually a degree symbol. And I'm just getting into a bad habit of doing this right now. But so the positive protons, neutral charged neutrons, and then negatively charged electrons. Yes? I forgot to ask, for the electron thing, like the mass, like 1 over 1,860, yeah. Do we have to know that? No. It's negligible. That's a good question, Alexander. You don't need to memorize that number per se. You just need to know it's negligible. Okay. Questions about that? Okay. So that's section 1, atomic structure. Just knowing the particles, calculating those ideas. Okay. The next section, relative atomic mass. Okay. Relative atomic mass is the fact that there are multiple isotopes of many elements. Okay, so the concept is that there are multiple isotopes of an element that exist. Okay, and don't forget, isotope, just as a definition, is the same atomic number, different mass number, or number of neutrons. I think both are acceptable for definition. Yes, Noah. No, that's a coincidence. Yeah. So yeah, in the auction example, that was just a coincidence that they're the same. It's not always the same. You can only calculate electrons based on knowing your atomic number and your charge. If the charge is 0, then it's the same as the proton number, and that's the only case. Okay. So isotopes are the same element with different number of neutrons, so the mass number changes. Okay, and because these elements exist in all these different mass numbers, we can't count every single atom of a sample of elements and say, okay, we need to measure every single individual atom. So what scientists did was they determined the abundance of each isotope. So they took oxygen and they took a sample of oxygen and said, okay, how many of these oxygen atoms are this isotope and how many oxygen atoms are this isotope? And they assumed that whether the sample was bigger or smaller than the sample that they tested, the ratio should be about the same. And yes, it's a little bit of an assumption, but it is generally true. They did a large enough sample that it's sufficient data. Yeah. And they used a mass spectra to do this, mass spectrometer. Now, you do not need to know how a mass spectrometer works, okay? You don't need to know how it separates the isotopes apart using physics and things like that. You just need to know that's what they did to separate all the isotopes apart so they could figure out the abundances. We will revisit mass spectrometer in topic 11 in data analysis and stuff like that. But so what this allowed us to do, because we had the abundance and we had the mass of each isotope, we could figure out the relative atomic mass, which is the weighted average of an element based on the abundances of the isotopes. There's a little bit more of a line as that well to that. Let me add that, but let y'all catch up. So weighted average of an element based on the abundances of the isotopes relative to carbon 12. So carbon 12 is our baseline for masses. So when scientists were trying to figure out, okay, what's an atomic mass unit, they used 1/12 of a carbon atom to equal one atomic mass unit. Okay, so because a carbon has 6 protons and 6 neutrons, and it's fairly easy to measure, they said, okay, well, whatever mass of a carbon atom there is, then we divide it by 12, and that equals the same as a proton and a neutron. So all these masses you see of atoms that are like 4 or 16 or 18.9, those are all relative to the mass of carbon 12. Okay. And to calculate this, you need to incorporate all the masses and their abundances as well. And so there is a formula for this. To calculate this. Now, you may have learned it differently. I'm going to show you the way I do it. And I do it this way to avoid mistakes because I think this is a fairly simple calculation, but there is room for error, and you don't want to lose a point just because you made a calculation error. And so this is what I do. Okay. So let's pretend I have isotope A of an element weighs 18 and it has abundance of 70%. An isotope B weighs 20 and has an abundance of 30%. Okay. To calculate my relative atomic mass or my average atomic mass, I would do this. I would do 18 times 70 plus 20 times 30. Add that all up, divide by 100, and that's my average atomic mass. Okay. Why do I separate out the 100? Because I think too many people move decimal points incorrectly. You know, I hate to say it, but everyone knows, oh, I just move it twice. But then what happens is sometimes students, when they see a decimal percentage, they forget to move the decimal point. Like if I told you the abundance was 0.001, 2%, sometimes students write down 0.2 and go, oh, that's already a decimal. It must already be right. When it's really 0.002 as a decimal form. And so then that messes up your whole answer. And so I do it this way. I think it's foolproof because you're not moving any decimal places. You're just trusting your calculator to divide everything by 100, and it always gets you the right answer. So I think that's kind of one of those places that you can minimize your mistakes by not trusting your brain to do something. I know that sounds silly, but it's something that you can do in your calculator. So I take the raw percent, multiply by the mass, add them all up, and divide by 100. Okay. You don't divide by 2 because you're not taking an equal average. You're taking a weighted average. So the 70% and 30% are already factoring how much abundance there is. The second kind of check and balance for this is when you do this kind of math and you have two isotopes that weigh 18 and 20, without doing any calculations, what should your average be close to? What should your average be close to? 18. Why? There's a larger percentage of isotope A because there's 70%. So this answer should be closer to 18. So if you get an answer like 21 or 19.4, you did something wrong. Again, these are the checks and balances you have to think about going, okay, maybe I typed in a decimal wrong in my calculator. Maybe I misread a number. Maybe I had a slightly dyslexic moment. I know I get numbers backwards all the time, okay? So you have to think, okay, my number has to be closer to 18 because my percentage of 18 is more than 20, so it has to lean that direction. Okay. Okay. Questions about that? Okay. Good news, that's the first half of topic 2 already. Okay, that's the majority of half of topic 2. The bad news is the second half of topic 2 is a little bit more information. Now, a lot of it is still review, but some of the stuff is new to IB chemistry, and I want to kind of stress it. So this is going to take a little bit longer for this. Okay. So this is the first, that was kind of like topic 2.1. Topic 2.2, the overall theme of it is electron configuration. But this is broken down into several subtopics to help A, explain electron configuration, B, talk about the origin of electron configuration, and then C, talk about how we compartmentalize the electrons and where we compartmentalize them. Okay. The first section we have here is something we call, question? No, I thought I saw a hand up out of the corner of my eye. So emission spectrum, okay? An emission spectra occurs when excited electrons, which means they go up to a higher energy level, return to a lower energy level and emit a photon as light. So when an electron gets energized, jumps up to a higher energy level, and then comes back down from that higher energy level, that excess energy it no longer needs is emitted as light. So you'll see kind of this diagram where you have like energy level 3 and then 1, and the electron will go down, and this photon will be emitted from that. And that photon is the difference in energy between that jump. Okay. Yes. Okay. So an emission spectrum gives off light. So an emission spectrum is what you would see colors of the rainbow when you look at a sample of an element, because they're emitting different visible colors of light and other frequencies of light as well, but what you see is the visible colors. Okay. And there's two types of emission spectra. There's a continuous spectra, or spectrum singular, spectra plural, is it shows all frequencies of light. Okay, so continuous spectrum is the entire rainbow of every single frequency of light. So it's essentially just a kind of a gradient of light. There's no missing parts of it. Everything is, all frequencies of light are shown. Okay. Okay. A line spectrum only shows specific frequencies of light. Okay. And those are more important to us because those specific frequencies of light are unique to each element. So a hydrogen line spectrum looks a little bit different than a helium line spectrum or a sodium line spectrum. And so this is a great identification concept. Okay. So that concept of line spectrum is what Niels Bohr did to experiment with hydrogen. And so what he did was, so this is Bohr and the hydrogen emission spectrum.
Do we need to know the name, or can we just, yeah?
I don't think you need to know that it was Bohr, but his name does come up here, like that. He's the one credited with it, but you don't need to know like the history of all the scientists like you did in 10th grade. Like you don't have to know Thomson, Rutherford, and stuff like that. Democritus and stuff like that. You remember like the timeline of the atomic structure, anyways. But Bohr is the one that came up with the hydrogen emission spectrum. Okay, I don't think they're asked what scientists came up with the hydrogen emission spectrum, if that's what they're asking. But he is closely linked to this because here's what he did. Hydrogen is great because it has one electron. So it's much easier to track the electron that's moving back and forth because there's only one. So they're not competing with any other electrons, it's not being repelled by other electrons. It's just one electron bouncing up and down between these energy levels. So what he did was this. He took a sample of hydrogen and energized it and looked at the light that was being emitted by that hydrogen sample. And what he noticed in that spectrum is he noticed like a red line, a green line, a blue line. Oops, that's too close. And a violet line. Okay. So we saw these four specific lines in hydrogen. Now, a couple things you need to know on top of that is that this diagram goes from lowest energy, which is red, to highest energy, which is purple. Okay. Now, the diagram may not always be like that, but in this specific diagram, lowest energy is on the right, which is red. Red is always lowest energy, so that's not a question. So violet is always the highest visible light energy, red is always the lowest, but it may be left to right, it may be right to left. Yes, Marina? Yeah, that's what we're going to get to later. Yes. So we will talk about how they converge once we kind of expand that concept out. Yes, correct. But yes, you do want to, yeah, she is right. You do want to notice that in this diagram, the lines are converging at higher energies. Like they're getting closer and closer together when you get higher energy. Okay. So here's the thing. Bohr saw these results and he had to come up with an explanation for this. Okay. And what this told him was, I'm only seeing four frequencies of light here. Okay. which means that these electrons cannot make every single infinite possible jump, because if they could jump whatever level, whatever amount they wanted to, I would see every single line. Because if there were no levels, then an electron could go up and down as much as they want, whatever amount, and you'd see every single line in here. But you didn't. You only see 4 lines. So what that told them was that it wasn't electrons could be anywhere they wanted to. They had specific levels or locations they could be posited at. Okay. So this evidence, this experiment told them that, oh, let me draw one more up here, that electrons couldn't exist anywhere. They could only exist on these certain energy levels. Okay. And therefore, only those jumps could happen, which are what shows these colors of light. Okay. And so jumps down to energy level 1, okay, would emit the most energy. And so those would be UV light, because UV light is higher energy than visible light. That's why UV light is very dangerous when it comes to sunburns and stuff like that, because they're higher energy than visible. So it actually does damage to your skin cells and things like that. Certain UV light. Okay. Oh, wait, red? Red. Yeah. So those are the colors. So you should know in visible light that red is the lowest energy and violet is the highest energy. Okay. Oh, n equals 1? Oh, sorry. Yes, n equals 1. Okay. Now, the jumps to 2 are where he saw the visible light. And so the smallest of those jumps would be your red line. The next jump would be the green line. And the next jump would be the blue line. And I didn't draw number 6, but whatever number 6 is would be that next jump here. So this was your visible. So n equals 2, whenever you jump down to n equals 2, that was visible. Whenever you jump down to n equals 1, that was UV. And if you jump down to n equals 3, that's the wavelength that's lower energy than visible. Does anyone know what that one is? Infrared. Yeah. No, higher than that. I just didn't draw the line in there. Sorry. Like there is theoretically n equals 6 here. Yeah, like the level up. Not yet. We're going to talk about that later. That's a higher level thing. Okay. So.
Wait, does the level it comes from determine what color of
yes,
light?
Yes. So like Tifa asked, the level at which it comes from determines the light that you see, because if it jumps from a higher level, you'll give off more energy when you come back down to that level. So which is why the violet color comes from a level 6 to 2 jump, whereas the red color comes from a 3 to 2 jump. Okay. Does that make sense, Tifa?
Yeah.
Okay. And I want to say this, every jump down to 1 is bigger than any jump down to 2. That's why even n equals 2 equals going to n equals 1 is UV light, and n equals 6 to n equals 2 is still visible. So like that difference between energy levels is significant at the lower ends, and it gets smaller and smaller as you go to the top. You don't need to know the names of these series of lights. Like you might see them in textbooks and stuff like that. You don't need to know Balmer, Lyman, and Pascal. You just need to know that UV light is n equals 1, visible light is n equals 2, and then infrared light is n equals 3, jumping down to that level. Okay. So this is where Bohr proved the existence of fixed energy levels. This is why Bohr's model of the atom has orbits around the nucleus, because his evidence, his laboratory experiment said, well, they have to be in orbits. They can't be anywhere around the atom. They have to be in fixed orbits that have fixed energies. And like what was said earlier, the energy levels converge at higher energies. So the fact that the difference in energy going from 3 to 2 and then 4 to 2 and then 5 to 2 increases, but increases by less and less each time, which is what we see here, tells Bohr that the energy levels are not equally spaced out. They are wider when they're closer to the nucleus, but when they get further and further away, they get more and more compressed, because the attraction is weaker out there. So the electrons have to try to get as close as possible to the nucleus. But then all the layers inside are repelling them, so there's kind of a equilibrium that's reached there. Yes?
What is UV light like the high
Uh,
like that? How is it different from the level?
Wait, what do you mean?
Like, so the energy levels converge like higher up.
Yes.
The lines. Like UV light, like you have it at the bottom and then like that.
Right. So that's a little bit different here, because what we're, well, okay, so the light that's given off is based on the difference in energy between the levels, right? The biggest difference between two levels is n equals 2 to n equals 1. So that jump is so much energy, it's categorized in UV. No matter what jump you go down to 2, that amount is still less than the jump between n equals 2 to n equals 1. So that's why, like, the emission of the light is UV when you drop down to 1, because that's the biggest possible jump there is. But what we're saying is that the energy of the energy, the energy level itself is higher as you go up. So yeah, so UV light's because of the difference in the jump, but the energy level state itself is higher. Like, yeah. Okay. Good question. Other questions about that? Okay. But so these are the main ideas that you want to take away from the hydrogen emission spectrum. The fact that energy levels converge at higher energies, the existence of fixed energy levels. Oh, I guess you should also add here, energy is emitted when electrons go down. It's absorbed when they go up, but it's emitted when they go down. Notice all these arrows are drawn downward as opposed to upward. Okay. Questions?
So can you simplify that converge?
Converge means to get closer and closer. So like n equals 6 and n equals 5 are closer to each other than n equals 5 is equal to n equals 4. So yeah, the gap should be smaller in energy.
Do you have to know how to draw that?
I don't think they'll have you draw the lines like horizontal lines, but I've seen on tests before where they give you the horizontal lines and ask you to draw an arrow of an emission that would generate visible light. So they might draw the black lines for you and then have you draw the line down to n equals 2 to show that you understand that that's visible light. So I don't think they'll have you draw the whole thing, but one arrow up and down is possible on a test. Okay. Other questions? Okay. Now, one last thing here, and I kind of mentioned it a little bit earlier, but I'm going to kind of isolate it here, is understanding the relationship between energy, frequency, and wavelength and things like that. Good news, SL doesn't have to calculate that. It's more of just a general understanding between these two ideas. And so, because yeah, if you look at the, let me double check, but if you look at the data packet here, these equations for energy of a photon, oh, actually, no, they do have speed of light and wavelength times frequency for standard level. So I will talk about that right now. Okay. So the relationship between energy, frequency, and wavelength. Okay. Understanding these ideas. Okay. For standard level, you have to know this equation. C equals lambda nu. Yes, those are Greek letters, and I'll tell you what each of those means. I'm sorry? Yes, it may be a sorority. Okay. C is the speed of light in meters per second. That's given to you in your data booklet, so you don't need to memorize that. Lambda is wavelength in meters. Nu is the frequency in seconds to the -1 or hertz. Those are both the same unit. So if they write hertz, that means seconds to the -1 is the same thing. It's one of those things where scientists just like to assign their names to a unit. A lot of units are named after scientists. Okay. So you have to be mindful of your units when you're plugging in values, because they might give you wavelength in nanometers or other units or centimeters, and you have to convert to meters to be able to calculate. So again, the first instance in our Saturday session where units really, really matter, because if you don't convert centimeters to meters, you're going to be off by a factor of 100, and that answer is wrong. There's no partial credit there. Okay. So you have to be able to plug in numbers. The real thing I want you to take away from this is the conceptual idea of the relationship between wavelength and frequency. Okay. And so what's the relationship between wavelength and frequency here? What's their relationship? Inverse. So there's an inverse relationship of wavelength and frequency, which means if your wavelength goes up, your frequency goes down. If your frequency goes up, your wavelength goes down. So know that general relationship here, because that's going to be important for standard level, especially is when you start talking about the energies of visible light, you have to know which ones have the highest wavelength, which ones have the lowest wavelength, and things like that. And so what you'll see is like red going all the way to violet. Red has the lowest energy, which means it has the lowest frequency. In higher level, you actually have to calculate the energy and the frequency based on their relationship with each other. In standard level, you don't. Oops, sorry. It has the lowest frequency, which means it has the highest. Actually, yeah, I should probably use the word longest because it's a length. Longest wavelength. Okay, so lowest frequency but longest wavelength. Whereas violet has the highest energy, which means the highest frequency, and then the shortest wavelength. So make sure you kind of understand that relationship here. Questions? Now, you'll probably get asked on the multiple choice because in the short answer, you actually are given the whole spectrum on the data booklet. So if you look at the data booklet here, the IB actually gives you the whole electromagnetic spectrum. So they're less likely to ask you about it in the short answer because it's already in the data booklet. So this is more of a multiple choice question where they like have you rank the different frequencies, like different like types of light based on frequency or wavelength and stuff like that. And so Gamma is the highest energy, and then radio waves are the lowest energy, but travel the furthest distances. That's why we use radio waves to transmit broadcasts and things like that, because they can travel very long distances with very little energy effort. Okay. X-rays are more penetrating. That's why we use them to like scan our bodies and stuff like that. But we also wear a lead vest on top because we want to protect our internal organs from that exposure to energy. Like when you're X-raying your ankle or like arm or something like that, you wear a lead vest because it will do damage to your internal organs if it's left exposed to it. Because X-rays are very high energy. But the three that I really kind of focus on here are UV, visible, and infrared. And if you know that red is the lowest energy and then violet's the highest energy, then you know ultraviolet literally means higher than violet, and infrared literally means less than red. So those three types of light are the ones you really want to know, and know that that translates to that. Okay. No, I wouldn't memorize those numbers. And they're in nanometers too, so that makes it a little bit trickier. But so I wouldn't memorize those specific numbers. That's a good question. It's not given, huh? Oh, is that how you remember it? Oh, okay. I didn't even think about that. Yeah, N is nanometers, so I guess it is 10 to the negative 9. I didn't even think about that as a way to remember it. See, I feel like if they give you nanometers in the problem, they'll tell you what the conversion is. Because if it was a conversion the IB really wanted you to know, they'd put it in this section here. Because all the conversions and stuff like that, like decimeters cubed to meters cubed or centimeters cubed, is given in here. So I'm going to assume that if they give it to you in nanometers, they would tell you what the conversion is. Now, if they give it to you in centimeters, that's implied. You should know that. But nanometers is centimeters to meters, not like nanometers to centimeters. So like you should know there's 100 centimeters in a meter. Okay, if you don't know that, I can't help you. But I think nanometers is a weird enough unit that they wouldn't expect you to memorize that. With my luck, this will be the year they expect you to memorize it. Okay. Okay. Questions about that? Okay. SL might run a little bit longer than I thought it was going to, but that's okay. HL will run shorter, I'm pretty sure. So it'll still won't go past 2. It just may be more SL than HL in this unit. But it's okay. All right. So that is emission spectrum. Understanding all that. Okay. Now, the next section we'll talk about is kind of the transition into electron configuration, which is sublevels and orbitals. Okay. So this is not electron configuration yet, but these are the ideas we have to apply to be able to write electron configurations, understanding these different ideas. Okay. Okay. So there are 4 levels of categorizing the location of electron. There is going from broadest to most specific. There is energy level, which is notated by the lowercase n. Okay. Okay. And this can go from 1 to theoretically infinity. Okay. And that is also exhibited on the periodic table as rows. So the 7 rows on the periodic table represent the 7 energy levels in which atoms exist. So 1, 2, 3, 4, 5, 6, 7. Okay. Within that energy level, you have what are called sublevels. Yes. Oh, the location of electron. So like you could say an electron is in energy level 2, but within energy level 2, there's more locations it could possibly be in. So we're being more specific as we go down. So within an energy level, there are a number of sublevels, okay? And those are recognized as S, P, D, F, etc. But we won't need to know anything further than F. Okay. And every energy level gains an additional sublevel opportunity. So the first energy level, n equals 1, only has S. N equals 2 has S and P. N equals 3, S, P, D. N equals 4 is S, P, D, and then F. So every energy level has the same number of sublevel letters as the number of energy levels they have. So if I say energy level 4, there's 4 letters, S, P, D, and then F. Within those sublevels, there is orbitals. Okay. And what that means is every S orbital and every P orbital and every D orbital represent an ability to hold 2 electrons. Okay, so 2 electrons in an orbital. Okay, and you do need to know the shape of a few of these orbitals, but I will talk about that in a second. So it doesn't matter if it's a P orbital or an S orbital or an F orbital, it can only hold 2 electrons each, no matter what. But because each sublevel has a different number of orbitals, it can hold a different number of electrons. So an S sublevel has 1 orbital, which means it can hold 2 electrons. A P sublevel has 3 orbitals, so it can hold 6 electrons. D sublevel, 5 orbitals, 10 electrons. And that keeps going down as many letters as you need to go. You add 2 orbitals every single time you go down to the next energy level. So F would be 7 and 14. Question, Sammy? Okay. So you need to know an S sublevel has 1 orbital, and every orbital can hold 2 electrons. So the number of electrons a sublevel can hold is just the number of orbitals times 2, no matter what. Okay. So that there's not like some change there. It's always true. An S sublevel is a sphere. Okay. It does say you need to know the shapes of the S and P orbitals, but it's not too bad, and I'll explain to you why. So S is a sphere. S for sure. Yes, Mateo. That's what we're going to talk about. Yes. So the P orbital has 3 orbitals, and they are divided by the axes on a graph. So there is an X. There's an X orbital. That's a figure 8. There's a Y orbital. That's a figure 8. And there's a Z orbital. That's a figure 8. So PX, PY, and PZ. But those are only shapes you have to know. You don't need to know D sublevel or F sublevel, just those 4. Yeah. As long as it's coming out toward you, doesn't really matter. Yeah. And so I just drew my Z axis that way instead of that way, but it's the same thing. Yes or no, Marissa? Okay. Now, a little bit of a mathematical formula thing in case you want to simplify a few things, okay? I guess for orbitals, yeah, you don't need the drawings. Only S and P. They're explicit about that. They say you only need to know the shapes of S and P. D and F orbitals become very, very complicated shape-wise, so you don't need to know those. But yeah, if you want to jot down that F sublevel is 7 orbitals, and 14 electrons, you can. But that's one of those things where there's a pattern, right? So if you know S, P, and D, then you can assume you know what F is. Minimize what you have to memorize. Okay. A nice little trick for an energy levels total orbitals is n squared. So if I don't care what letter the orbitals are, I just want to know how many total orbitals are in energy level. I just square that energy level number. So if you think about it, energy level 1 is 1 squared, 1 orbital. Energy level 2, 2 squared is 4 orbitals because it comes 1 from the S, 3 from the P. Energy level 3 has 9 orbitals, 1 from the S, 3 from the P, and then 5 from the D. So that is always true. So if I give you energy level 10, there would be 100 total orbitals in there. Would you have to label all of them? No. But that just could be a question on the multiple choice. They might say, if n equals 6, how many total orbitals are there? Now, you could do it by hand and go, well, like sublevel 1 has 1, then 3, 5, 7, 9, and 11, and add it all up. If worst comes to worst, but you could also do 6 squared is 36 orbitals. Okay. All right. Now, because every orbital can hold 2 electrons, if you want the total electrons in a sublevel, it's 2n squared, right? Because if every orbital can hold 2 electrons, then it's just times 2. So if I ask energy level 8, it would be 8 squared, which is 64, times 2 is 128 electrons. Questions about that? Okay. All of that translates into our electron configuration because we had to know what S, P, D, and F are. We have to know what energy levels are. And we have to know how many electrons can be placed in each one. And so this next subsection is electron configuration. Yeah, yes, for topic 2. Ooh, topic 3. Okay, this is gonna be long. Okay, so yeah, that's true. I don't think we'll do as much higher level this week as we may not get into transition metal chemistry but that's okay because you haven't seen it before anyway, so it may not make much sense to you. So this may end up being a 2-hour SL and then 1-hour HL. Sorry, Marina. Okay, electron configuration. Okay, whenever you write electron configuration, there is a notation for it. And there's 3 parts of that notation that you have to be familiar with. Okay. That big number in front, or the coefficient, is the energy level. This exponent is the electrons in said sublevel. And this letter S is the sublevel that we're discussing. Okay. So every block of electron configuration that you write has to involve an energy level, a sublevel, and how many electrons are in that sublevel. Okay. And we read electron configuration using our periodic table by reading it kind of left to right. Now, what's great about the periodic table is that it's actually broken down into sublevels visually, okay? And so if you look at a periodic table, a blank periodic table, the S sublevel can hold how many electrons? How many electrons can the S sublevel hold? 2. Is there a part of the periodic table that is 2 blocks wide? These right here. And so guess what? That's the S sublevel. P can hold how many electrons? 6. Is there a section that's 6 wide? The one on the right. This is your P sublevel. Okay. D can hold 10. Guess what? The middle is 10. So if worse comes to worse and you forget how many electrons can be held in each sublevel, if you know where they're located on the periodic table, you can just go, okay, how many blocks wide is it? Yes, Marina. Oh, false alarm. So, and then F is also down here, and it's 14 wide. So if you were running into the situation like, oh my gosh, how many electrons can be held in P? Well, P is on the right of the periodic table. That's 6 boxes wide. That's how many electrons can be held. And then how many orbitals is that? Well, 6 divided by 2 is 3. So P can hold 3. P has 3 orbitals. So there is a lot to the periodic table structurally that tells you information. That way you don't have to memorize it and stuff like that. Or if you forget something, you can fall back on it. Okay. And this is what I've always been saying is like always have a way to reason something out in case you forget it. You know, because anytime you memorize something, you are trusting yourself to memorize it correctly. And there's no way to check your answer if you're not sure of whether you memorize it correctly. So every time we talk about memorizing something other than organic chemistry, which is kind of all memorization, but anytime we memorize anything else in chemistry, there has to be a reasoning behind it and go, okay, this is why that makes sense. Okay. And so that's what we focus on when we're trying to minimize what we have to memorize. Okay. And so the energy levels are 1, 2, 3, 4, 5, 6, 7. Actually, you know what? I'm not erasing this. I'm just going to highlight it instead because I think that's easier for people to see later on when they look at the notes. Because the circling was kind of like all over the place, and there was some inaccurate. Yeah, maybe that's the best way to describe it. Okay. Yeah, that's better.
Mr. Chong, is the one in
Yeah.
the top right corner not part of the P sublevel?
Yes, Pran, that's a good question. This up here is actually the one block on the right that's S, because the first energy level only has one S2, so this is considered one S2, right, Pran? Thank you. But everything else is purple. Okay. So we read going across. Now there is one exception to the rule that you have to know. The D sublevel starts in energy level 3, but it's in energy level 4, because what happens is you fill 4s1 and 4s2, oops, before you fill in 3d1 to 3d10, and then you go back to 4p1. Okay. So the reason why that is because 4s, even though it's on an outer energy level, it's actually lower energy total than 3d. Now you don't have to really explain this. Like you're not gonna have to explain this on short answer, so I'm not gonna go too much detail about this. But you have to fill in 4s before you fill in 3d. So that is something you do want to know, that like if you're going 4s, 5s, 6s, whatever, D has to be one less than that because the whole D block is shifted down based on the way the electrons fill. So it's always one less. So it's if this is 5s2, then this is 4d1. This is 6s2, then this is 5d1. Even though you're not going to go that far in electrical configuration, that's true. Yes, Lamar. The F actually goes down by 2, but we never go into F in the IB, so you won't have to worry about that. I mean, I'm sure you've thought F the IB, but not in this case. Sorry, we'll edit that out. I'm not editing any stuff out. I'm not going to spend time on doing that. Okay. So let's say you have an element like this right here, and I marked an X right here. It doesn't even matter what element it is, to be honest, because that doesn't really affect the electrical configuration. You're going to read it off the periodic table as if there are no elements there. You would start at the beginning here, and you get to this point. So it would be first 1s2, element X. And then you go here, and this becomes 2s2. Like, actually, it's selenium, Se. But, like, you don't need to know that. Oh, okay. Well, I mean, what I'm saying is that even if the periodic table were blank and they just labeled like unknown element at this box of the periodic table give the electron configuration, it wouldn't matter whether it was selenium or not. Does that make sense? Yeah. Okay. So 2s2 and then 2p6. Then 3s2. And so you keep going to the end of every section until you get to the element in question. So here, which is 4p4. So this would be considered the full electron configuration of that element, okay? One of the ways you can check this is add up all your exponents, because all your exponents should equal the number of electrons that atom should have. So the sum of the exponents should equal the atomic number, okay? So if I add this up, 2, 4, 10, 18, 20, 30, 34, selenium should be atomic number 34. If it's not, then one of my exponents is wrong, or I didn't count enough boxes. Okay. Okay. Questions so far? Oh, sorry, I'll scroll up a little bit. Now, you can also do noble gas configuration sometimes. Be careful. If the question says state this full, you cannot write noble, it'll be wrong. So part of the question, part of understanding instructions is making sure you provide the right answer they're asking for. So this is full. Noble gas configuration takes the last noble gas that you pass before you get to that element and use that to abbreviate everything else before, because it's really not important. All that stuff before is not super important. In this case, that's argon. 1s2, 2s2, 2p6, 3s2, 3p6 is argon. And then the rest of it is 4s2, 3d10, 4p4. And that's noble gas configuration. So it's the noble gas that you pass last, and then you write the rest of it after that. But they have to allow you to write that for your answer to be acceptable. Yes. Correct. If they don't specify, if they just say state the electrical configuration, that should mean they are allowing both. Correct. Yes. We are, and we're about to do that in a little bit. Okay. Now, the good news is that if you can do electron configuration, you can do the arrow diagram, because really all you're doing is translating the electrical configuration into arrows. That's all you're doing. And we'll talk about that in a second, because that is something we need to know. But there's more to electron configuration than just this. Okay. All right. All right. So electron configuration, both of those. Okay. Now, there are a couple of exceptions that you need to know that don't follow exactly the trend of reading electron configuration. And those two are chromium and copper. Okay. Chromium, copper, if you read them normally, you would get chromium would be, and I'm going to do abbreviation because it's just easier, 4s1, 3d4. And for copper, you would get 4s1, 3d9. Oh, sorry, 4s2. I'm sorry. I was like mixing up the right value and the wrong one at the same time. Okay, 4s2 3d4 and 4s2 3d9. Sorry, I was like, how am I going to move electron over without? Okay, anyways. So that's the way you would think it would be normally written. But what happens is one of the electrons in the 4s goes over to the 3d to fill it because the energy states of those sublevels are relatively similar. And so what it ends up being is AR 4s1 3d5 and AR 4s1 3d10. So only for chromium and copper, where you could move one electron over to either half fill the d sublevel or fill the d sublevel, does that occur. No other transition metal, like you don't ever move 2 over, you don't ever move 1 over to get any other number than 5 and 10. Those are the only 2 exceptions you have to know. The, to a generic idea. So the idea is to half fill or fill D sublevel, but S is still half full. No, we're gonna get that in a second. I know those yes, there is a rule about like low energy states of half filled and full and stuff like that. But that's more for the orbital diagram. We'll talk in a second. Okay. So do know those exceptions for this. Why does it not say ions in here as well? Oh, and ions. It does say ions. Okay. Now, electron configuration can be written for atoms or ions. So you have to be able to manipulate electron configuration to get to an ion. So for example, let's say Na is 1s2, 2s2, 2p6, 3s1. Okay. Electron configuration tells you several different things. Okay. And namely, one of the things that it tells you is valence electrons. Valence electrons are the outermost electrons in an atom, which means highest coefficient. Doesn't always mean the last number. It just means the highest coefficient present. So for example, here, Na has 1 valence electron. Okay. And these valence electrons, wait, what, Chloe? Yeah. No. There's 1 valence electron in the highest coefficient of 3s. Okay, yeah, sorry. So the coefficient is 3, the highest coefficient in Na is 3, and the third energy level only has 1 valence electron. Sorry. So it's 1 valence. Yes, Lamar.
So if you have, for example, chromium, do you only have 1
Yep,
valence?
correct. And that's where we're going to get to know, because that's where the IV tries to catch people that don't fully understand exceptions in transition metals and valence electrons. Yes.
And what would we do if there was, say, an ion that had like the same issue with chromium and copper, like how
No. Oh, that's a good question. You don't ever do exceptions for ions. So you would never move an electron over to balance that out. No. So even if you got like an ion that formed like 4s1 3d4, you would, or 4s2 3d4, you would never move one over.
so everything would work.
Correct. Everything else would work. Everything here would work normally. So Na is a metal, so it loses electrons, and it's going to lose its valence electron. So Na plus is just 1s2, 2s2, 2p6. Okay. Oxygen is 1s2, 2s2, 2p4. So the highest coefficient is 2, so it has 6 valence electrons. Well, we know oxygen wants to gain 2 electrons, so we're going to put those electrons in the highest shell, which the available space is in 2p, because 2p can hold up to 6 electrons, so we'd put the electrons in there to make 2p6. Okay. The thing that Lamar was saying, and Mateo was kind of asking as well, is transition metals is where they kind of trick you. Like, I know they don't really trick you, but that's where the mistakes get made, because when you look at copper as an exception, even too, this is where it's challenging. So copper is AR 4S1 3D10. Okay. Actually, copper 1 plus means you lost 1 electron. Where do you lose that electron from? 4s. So just because it's not written last doesn't mean it's not a valence electron. That's why you have to really pay close attention to it. So Cu is just AR 3D10. And the reason why the IB loves asking about Cu plus is because you need to know several things to get that right. Because if you don't know Cu is an exception, but you do know you lose from the outermost shell, you'll still get the wrong answer. If you don't know the exception and you don't lose from the outermost shell, you get it wrong. You have to know both that it's an exception and that you lose from the outermost shell to get this. So it's a very popular multiple choice question. They'll say, what's the electron configuration of copper plus? Because there's so many opportunities for students to make a mistake to get it wrong. Okay, so let me jot that down. Lose from highest energy level. Not necessarily the last thing you write. Some books will have you rearrange it so that 4s1 is last, but I don't like that because I like to think of it in the order in which they fill, which is 4s and then 3d, and so I write it that way. But a lot of textbooks will sometimes write 3d, 10, 4s1 in that order so that students think the last ones are always lost, but I don't like that concept. Correct. So Cu2 plus is AR 3D9. But again, if you're a person that doesn't know the exception, you could still stumble into this question, right? Because like, if you think Cu is 4s2 3d9, but you know that you lose valence electrons first, you would still get 3d9. So that's not a good question in the IB's mind, because someone that doesn't understand it completely could still get it right. But remember, you're trying to differentiate students and their abilities. And so they usually don't ask about Cu2 plus because you could stumble across the right answer without knowing every single aspect of it. But Cu plus, very popular multiple choice question. Okay, questions about that? Okay, well, this is okay. Now, orbital diagrams. Okay, orbital diagrams are just visualizations of the same thing that you're writing electron configuration, but now there's no such thing as just P6. There are 3 P blocks that you have to put electrons into, and this is what Marissa was asking about earlier about the 3 rules that you have to follow when you fill in electrons. Okay, so let's say we have copper, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Well, drawing the appropriate number of boxes is the first thing to do. S is 1, because S only has 1 orbital. So every S that you have should only have 1 box. P has 3 orbitals, so every P should have 3 boxes. And D has 5 orbitals, so you should draw 5 boxes. Yeah, they call them box and arrow diagrams. Yeah. Orbital diagrams or box and arrow method, either way. So establishing the boxes is the first step in drawing the orbital diagram. Okay. A lot of times I think the IB will provide these boxes for you already, so that might save you some trouble. But there are 3 rules that you have to follow, and they state them by name here, so I'm thinking that you have to know these names. Like in their syllabus, they state them by name. And so the first rule you have to fill out is called the off-bow principle. Okay. No, I would. Because unlike other things, they say application of the off-bow principle, Hund's rule, and Pauli exclusion. So I would know those rules. Like I would know the names here. Okay, the off-bow principle states that electrons fill the lowest energy orbitals first, meaning that they fill in 1s before they fill 2s, before they fill 2p, before they fill 3s, they fill 4s before 3d. That is the off-bow principle. The second rule is Hund's rule, stating that, and I'm going to kind of paraphrase this. You don't need to there's not like a exact definition, but I think this is the best way to describe it. When multiple orbitals are in a sublevel, each orbital gets 1 electron before any get 2. And you do this to minimize electron-electron repulsion. So if you have a p sublevel that has 3 blocks and you have 3 electrons to distribute, you put 1 in each before you put 2 in 1. Oh, because remember, electrons are all negatively charged. So if they're close to each other, they repel each other, which creates more energy requirements to hold them all together. So you keep them apart so that they don't interact with each other, so that the whole state of the atom is lower energy. Yeah. Maybe we won't get to topic 3 today. Because we're already at 12:30 and we're kind of wrapping this up. Maybe we won't get to topic 3 today. Because topic 3 is a lot of stuff. I could go from 12:30 to 2 on just topic 3. Okay. The last rule is the Pauli exclusion principle. Okay, and there's 2 aspects to this. Okay. Each orbital holds a max of 2 electrons of opposite spin. And both of those concepts are crucial to the Pauli exclusion principle. Mateo, do you have a question? Okay. Oh, sorry, I'll leave this up for a second while y'all write this down. Okay. So I like to apply this when I'm filling in, even from the very beginning, just to get into the habit of doing it so I don't mess up at the end, because I don't like to hastily put stuff in. I know some kids will just go, oh, this is full, I'm just going to fill it in. I like to follow all of these rules every single time so I don't make mistakes. So I want to imagine it like there are walls at every single sublevel, and all of them need to be filled before I move on to the next one. So 1s2 looks like this, and I draw half arrows here. So I don't think they care specifically about this, but I generally have been told that half arrows are 1 electron, so I draw them like this. Up, down, opposite in the same orbital. 1s, up, down. 2p6, I go 1, 2, 3, 4, 5, 6. So I fill the top ones first, and then the bottom one second, the downward one second. 3s, up and down. 3p, up, 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 down, down, down. like I said, it's not necessary, but again, it's just to get me into the right habit. So when I get to 3D10, I don't, or 4S1, I don't make a mistake. So 4S1 is only 1. And 3D10 is 5, 6, 7, 8, 9, 10. That's the orbital diagram of Cu. And orbital diagrams help with periodic trends a little bit, and we'll talk about that next time, and we're not going to talk about today. Because the arrangement of electrons in the sublevels actually affects how periodic trends work. And like when you have ionization energy exceptions or electron affinity exceptions, that's because of the way the electrons are oriented in orbital diagrams. And so when we talk about trends, when we talk about exceptions, I'm going to refer back to these orbital diagrams to explain why nitrogen has a higher ionization energy than oxygen. It's because of the way the electrons are oriented in the 2p sublevel. And so we will talk about these again in topic 3. Okay. Questions? Okay. You've just gone through a crash course in all of topic 2 for SL in an hour and a half. Okay, so we are stopping now for SL. We're going to take about a 15-minute break, or maybe let's say 10-minute break because we went a little long. At 12:45, we will continue with HL stuff for topic 12. Go. Okay, so higher level topic 12 is what we're going to add into the notes here. Now, higher level topic 12 isn't actually a lot of material here. It's really 2 major ideas. There's calculations and there's how we use ionization energy to prove the existence of aspects of the atom. And so in SL, we talked about how Bohr used the hydrogen emission spectrum to prove the existence of energy levels. But it turns out if we use ionization energies, we can actually prove the existence of sublevels as well as energy levels. And so if we go back to this diagram that we were talking about before with the emission spectrum, okay, ionization energy is the energy required to be absorbed to reach n equals infinity, which is the out of the atom.
Sorry, can you say that again one more time?
Sure.
The definition.
Yeah, I'll write it down. I'll jot it down too. So ionization energy is the energy absorbed by an electron to leave an atom. Okay.
On the IB exam, could they potentially ask for definition?
I don't think they'll ask you for a definition of ionization energy. Okay. We will talk about the definition of ionization energy a little bit more in topic 3. But in this diagram, in this context, this is what we want to think of it as. So if they ask you to draw an arrow to represent ionization energy, your arrow should be from energy level 1 up to and not past n equals infinity. So it should stop at n equals infinity. Don't draw a line through n equals infinity. Just stop it at n equals infinity. They are actually really OCD about that and say if the arrow goes past n equals infinity, then do not accept it. Because n equals infinity is the end of the atom. Okay. I think if the IB will provide you with that and they will draw the n equals infinity for you. So you shouldn't have to draw it. That's a good point. Okay, they'll like do n equals 1 to n equals 6 and then n equals infinity on top of that. So just draw the line up to that point. Okay. Now, here's the idea with this. Okay. And I'm sorry, but this part you're not going to be able to copy down because it's a giant table of data, but you may want to jot notes about this. Okay. So if we measure the ionization energies of an atom and an ion of that element, we will get a list of data that looks like this. Okay. And the first ionization energy is the first electron loss, and the second, third, fourth, and fifth are consecutive ones after that. And this table you don't need to memorize, but it is something you need to understand because this data proves the existence of a variety of different things. Okay. One, it proves, proves existence of energy levels in a couple different ways. Yes, because if you notice, especially in the first ionization energy levels, you notice a pattern here, right? If you notice, after helium, there's a big drop down. After neon, there's a big drop down. Those drop downs represent a change in energy level because it's getting further away and it's starting a new energy level. So it's easier to lose that one electron than it was to lose one of the 8 in the inner shell. So the idea that the energy level the ionization energy drops whenever you go to a new energy level is part of why we know there's energy levels. Okay. And if you graph them, you'll see that. Like a lot of times they'll say like, what does the graph of ionization energy look like? It'll look like up 2 and then drop down. And then it'll go up, 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 and then drop down. And then up, 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 and then drop down. And so you do want to understand that ionization energy as a general trend increases as you go across, but there are dips every time you change energy level, and there's sometimes exceptions, which we'll talk about in topic 3. Okay. You could also see this within an atom because remember, valence electrons are on a different energy shell than inner electrons. So if you look at boron here, there is a gigantic jump between the third ionization energy and the fourth ionization energy right here. Okay. What that tells us is these 3 electrons are valence electrons. So the biggest jump in ionization energy for an element as you go across tells you where the energy level changes. And when I say biggest jump, I mean biggest difference. I don't mean like a factor or multiplier. I mean just biggest difference. Because yes, 32,000 to 25,000 is 7,000 difference, but 25,000 to 3,000 is a 22,000 difference. And that's a bigger jump, a bigger difference. So this tells us boron has 3 valence electrons. Okay. So whenever you're given an unknown element or an element, and you're given their successive ionization energies, you look for the biggest jump. And all the ionization energies before that are the valence electrons. Carbon, again, the biggest jump is after 4, which means carbon has 4 valence electrons. Questions about that? Obviously, you can't see fluorine because we don't go to 7 and 8, so you don't see that jump, but it is there if we went further on this table. The second thing is it proves sublevels existence. Because within some of these elements, you can see a smaller, big jump, but within the energy level. Okay. Okay. So with nitrogen, you see the big jump after 5, which makes sense because nitrogen has 5 valence electrons. But there's a slightly smaller big jump that happens right here, a 3,000 jump where none of the other ones are a 3,000 jump. And what that tells you is that these are p electrons and these are s electrons. Okay, so the biggest jump is always the the energy level, but the second biggest jump is let me write this down here, just so like y'all can write this down, because I do want to label this. Okay. So if this is N, this are our valence electrons, because this is the much bigger number, bigger jump. But within those valence electrons, you notice that there is a slightly bigger jump than usual between these two, between 3 and 4. And what that tells you is, because nitrogen is 1s2, 2s2, 2p3, these first 3 must be the 2p3 electrons, and these next ones are the 2s2 electrons, and these must be the 1s electrons. So we're losing from the outermost shell, but then also the outermost energy sublevel as well. Okay. Yes, it should be. It should be, like, I would say it should be bigger than like the next jump after it, which makes it weird because it should always be an increasing difference. But when there's a bigger jump than it should be, that's your kind of tip off. Yes, Marissa. Right to left. Yes, trend wise, but there is a blip where you change sublevels, and there's a yeah, there's a little blip when you change the difference energy. There's a little blip. Wait, okay, hold on. Let me process for a second. So I would always read it left to right here. And so it should always constantly increase ionization energy wise. But the difference in the increase should tell you when there's a change in sublevel. And the biggest jump of an increase in ionization energy as a whole tells you when the next energy level changes, which tells you when the valence electrons stop. Is that your question?
Well, I mean, I was just asking because if there's a significant difference
Oh, there's a significant difference. Yeah, like there will never be a confusion between the 2p to 2s versus a 2s to 1s. There will never be yeah, it'll be very, very obvious. Yes. Yeah, and the IB will do that intentionally as well, even if they make up the numbers so that it's obvious. Okay. The biggest jump is always energy level jump. And so if the IB didn't tell you that this was nitrogen and just said an unknown element had these ionization energies, you should be able to, by looking at these numbers, know that the element is in group 5 or 15, I should say, because it has 5 valence electrons. It doesn't have to be N, it might be a different element in that group, but it is 5 valence electrons here. Questions about that? Okay. Yes.
Yeah, so I think, I don't remember like the specifics, but there were like some sort of like exception questions last year, where it was like, it would be easier if, it's like,
I know where exceptions you're going with, and that's with ionization energy trend, which we'll discuss in topic 3. So I know what you're saying, because if you look here, you see nitrogen's higher than oxygen, even though oxygen's supposed to be higher. That is a periodic trend question, not a using ionization energy to determine sublevels. So yes, we will do that in topic 3. Yes. So that will be covered later on when we talk about trends. That's a good question, though. Okay. Second part. Calculations. Okay. Oh, it actually does say explanation of trends and discontinuities, but I'm going to save that for periodic trends because it makes sense more there, I think. Okay, calculations. Okay, yes, in SL you have to know this one, but in HL you have to know this equation as well. So in SL, you just have to know the relationship between wavelength and frequency. But in HL, you have to know the relationship between energy and frequency as well as frequency and wavelength. So this is the energy of a photon. And you have to incorporate H, which is a constant known as Planck's constant, to do this. And it's 6.63 times 10 to the negative 34th joules times seconds. My J's always kind of look really bad.
Is that in the data booklet?
Yes, it is in the data booklet. Yes, that's a good question. It is listed in the data booklet in this section right here. Planck's constant H, 6.63 times 10 to the negative 34 joules times seconds. Yes. They do give you the formula as well. So in 12.1, it's right here, E equals H nu. Okay. And again, all the SL formulas are given first, and then all the HL formulas are given second in the data booklet. So just keep that in mind. So if it's an HL idea, they're all after 8.3. All 12, 15, 16, 17, 19, that's all HL in this. So just remember that when you're looking for equations and stuff like that. Okay. So the idea here, what I find them trying to do here is a couple of things. You might be given the frequency and just asked to calculate the energy of the photon, but the hardest question I think they do is this: energy of a photon for ionization energy. They'll ask you, like, what energy of a photon is required to cause an electron to be lost from an atom? It's a dot, multiply, it's times. Sorry, it's times. That way the units cancel out because seconds times seconds to the negative 1 gets you just joules. The reason why this is tough is because they'll say use the data booklet. And what you see in the data booklet is this. You can go to ionization energies for elements, like right here. And let's say we see phosphorus is 1012 kilojoules per mole. Okay. So phosphorus has an first ionization energy of 1112 kilojoules per mole. The thing is, though, the problem is this is per mole of phosphorus. And they don't want a mole of photons, they want one photon to one atom of phosphorus. So you have to convert this value into per atom and not per mole of photons. So you have to change this and divide it by 6.02 times 10 to the 23rd atoms of phosphorus. To get the kilojoules per one photon. Let me get my calculator out and calculate that. So 1012 divided by 6.02 E negative 23. Oh, sorry, just E 23, not negative. Gets you 1.68 times 10 to the negative 21 kilojoules of energy needed for one atom of phosphorus to lose 1 electron. Okay, so that's your E. So can we now plug that into the equation? Can we plug that into this equation now and figure out the frequency of the photon? Why not? It's in kilojoules. Again, this is where units are a huge factor, and why I always emphasize writing units down, because a lot of students will say, oh, that's energy, I'll just use that number, and they'll be off by a factor of 1,000 when they get their answer. This is why I tell you to write units for everything, because this is 1.68 times 10 negative 21 kilojoules. So you have to multiply by 1,000 to get it to joules. So this is actually 1.68 times 10 to the negative 18 joules is equal to 6.63 times 10 to the negative 34th joules times frequency. So then we divide by 6.63 e negative 34, and we get a frequency of 2.54 times 10 to the 15th seconds to the negative 1. And you'd be surprised how many kids get 10 to the 18th because they did, or 10 to the 12th because they didn't convert to joules, or they divide the wrong way or multiply the wrong way. Frequency should generally be a positive exponent. I'll tell you this right now. Frequency is generally a positive, like 10 to the 12, 10 to the 15, 10 to the whatever. So if you're getting 10 to like negative 54 or something like that, you forgot a negative exponent somewhere. Like you might have divided by 6.63 times 10 to the 34th instead of negative 34. You shouldn't get an exponent of like negative 50 something. So I guess the energy of the photon is 1.68 times 10 to the negative 21 kilojoules. I should have really said the frequency of a photon for ionization energy is that. So that's kind of my mislabel here. But that's where students struggle, because they don't pay attention that ionization energy is measured per mole, and a photon only attacks one atom at a time. So the frequency of each photon has to be this amount. Okay, so you have to convert your ionization energy to per atom before you can calculate the energy of the photon. So again, units matter a lot. You're going to hear that in every Saturday session that we go over with, is units matter a lot, and writing them out will save you hopefully a lot of mistakes, because that's really like higher level aspect of this class is mostly math, like whether it's Rice charts, whether it's energy of a photon or frequency of a photon, whether it's rates of reaction and stuff like that, and exponents in that case, or equilibrium. It's all about units, or Gibbs free energy, entropy, all that's unit based. And if you can write your units down, you're going to save yourself some points and some heartache when you're 1 mark off from a 7 or 1 mark off from a 6. Okay. And you can convert that to wavelength as well, because once you have the frequency, you can convert that to wavelength in meters by using the same equation that you did before. C equals lambda nu, and it's 3.00 times 10 to the 8th meters per second is equal to lambda times 2.54 times 10 to the 15th seconds to negative 1. And you get a wavelength of 1.18 times 10 to the negative 7th meters for your wavelength. Okay. Questions about that? Okay. Like I said, the high level aspect of this is not a huge amount. It's the calculation and understanding what ionization energies can tell us, and that's it. Topic 2 is pretty hefty when it comes to the content relative to SL versus HL. Okay. That's your abridged version of topics 2 and 12 complete review. So we did it in about 2 hours and 15 minutes. So I would tell you in class, if I was teaching this first time, it would take about a week and a half, 2 weeks to cover all this. But this is kind of the clip notes of it. So I'm going to stop recording right now.